Hello everyone. So today we are solving another interesting problem number 39 combination sum, and the problem says given an array of distinct integers candidates and a target integer target, return a list of all unique combinations of candidate where the chosen number sums to target. You may return the combination in any order. Okay. The same number may be chosen from the candidate an unlimited number of times. Okay. Two combinations are unique if the frequency of at least one of the chosen number is different. The test cases are generated such that the number of unique combinations that sums up to target is less than 150 for the given input. And let's check our constraint. Candidate length will be maximum up to 30. Candidates elements would be from 0 from 2 to 40. Okay, and all the candidates are distinct. That's a good point. And target would be between 1 to 40. Okay, so to solve this problem, what we can do is we can create one function and traverse down the candidate list and pick that element one by one and see if it matches, if the element that we are picking sums up to the target that we are looking for, and if yes, then we'll accept that candidate list, and if not, then we'll reject it. So here we have our candidates like this: 2, 3, 6, 7, and we'll start with one path list. Okay, and we'll go down every path that we encounter. So first we'll go and pick 2, then we'll again go and pick 2 inside this. So we have two twos. Then again we'll go and pick this 2. So 2, 2 and 2. Okay. And the maximum that we can go is up to the length of the candidates, because after that we don't have any element to pick. So here we have 2, 2, 2 and 2. So once we have reached till the, so we want to go up to n, right? So here we'll check the sum. If the sum is more than the target, then we want to return back. And here we will again open one more branch and we'll check for the next element. So this is the next path sum, which is going to be equals to 9, which is again more than 7. So we'll return back and we'll again open one more branch for I equals to 2, like we are picking the element at the index 2, and we'll see the sum. So 2, 2, 2 and 6. So again, because we know we cannot go with these sums, we'll return. So we got one condition over here that if my sum of path is more than the target, then we'll return back. And so we'll prune all these branches and we'll go back and check for the uh, next element that we have over here. So in this case, what we want to do is we want to pick 3. So when we pick 3, the sums become 7, which we want in our list. So we'll append this list into our result. So this will go into our result and we will explore other branch. so it will give us 2, 2 and 6. So this is becoming more than, sum is becoming more than the target, so we'll return back. So one more condition that we saw is if my sum is equals to path, then sum is equals to target, then also I will return back. And similarly, we'll explore all other branches. For I equals to 1, we'll start with 3. For I equals to 2, we'll start with 6. And for I is equals to n minus 1, which is basically up till the number of elements in the candidate list, we have the element. So what our function is gonna look like essentially is we need this. Okay, so let's put this aside. Okay, so here is what we discussed. Like, we need to decide our function, and we'll pass one list into it. This is one integer, this is one path list, and for my I, which is going from up to n, what I want to do is I want to keep adding that candidates into my path list, right? And if my sum of that path has become more than the target, then I want to return. And if my sum is equals to sum of path is equals to target, then I want to return. But here, when I am returning, I want to add all these paths that I have traversed into one output list. Okay, so this is how we'll write our function. So this is how we can write it down. So let's start. So we need one output array to hold our results, and n is the length of candidate lists that we have. And we have one DFS function which we need to define, which will have all the paths that we're going to traverse, and we'll start our DFS from starting, which is 0 with an empty list, and at the end we'll return this result which will have our everything. So like we decided, we'll go into the function one by one from s up to n, and we'll traverse into our DFS function with the I that we have, and the path plus candidates that we are gonna pick one by one. Okay, so and the terminal conditions for this recursive function, that if my sum of path is more than target, then I want to come back. So we'll return in that case. And if our sum of path is equals to target, then we want to add this into our output list. Okay, so we'll return in this case also. Okay, so everything looks good, and let's run our code. Okay, so let's run our code for another example test cases and see how it performs. Okay, so it is accepting both the example test cases. So now let's submit our code and see how will it do. Okay, so it has been accepted and it is pretty good. So coming to the time complexity for the problem, so the time complexity would be the number of candidates that we have. So the number of candidates is like n, so n raised to t target that we have. Target is 1 basically. So O of n raised to something, which is these basically O of n raised to target. So that would be my time complexity. And space complexity is we are having the elements up to the target. So this would be O of target, like the number of target that we have. So yeah, this would be the time complexity and space complexity, and that's how you solve this problem. Thank you.